Beneath one of the most inhospitable landscapes on Earth lies an ocean, not metaphorically, not poetically. An actual body of water, larger than all the Great Lakes combined, has been sitting here, untouched, for up to 1 million years. In the 1950s, oil companies drilling for crude discovered it by accident. They were looking for black gold. They found something far more valuable in a desert nation: fresh water. And in 1984, one man decided to bring that water to the surface, through a network of pipes so large you could drive a truck through them. This is the largest civil engineering project in history, a 4,000-kilometer underground pipeline network, $25 billion, and a question that haunts it to this day. What happens when the water runs out? Libya is 90% desert. Rain falls on just 5% of its surface. There is not a single river that flows year-round. And yet 78% of the population, nearly 5.5 million people, live concentrated along the Mediterranean coast, in cities like Tripoli, Benghazi, and Sirte. By the 1970s, these coastal aquifers were collapsing. Seawater was seeping into the groundwater. The wells were turning salty. Libya faced a choice that seemed impossible for a wealthy oil nation: import water from Europe by tanker ship, build expensive desalination plants along the coast, or do something no one had ever attempted at this scale. On August 28, 1984, the Libyan government chose option 3. The plan: drill over 1,300 wells into ancient aquifers deep in the Sahara, pump the water to the surface, and transport it through an underground network of massive pipes across distances up to 1,600 kilometers to the cities of the north. They called it the Great Man-Made River. The first engineering challenge was deceptively simple in concept and staggering in execution. How do you build a pipe big enough to move 6.5 million cubic meters of water per day? The answer is a technology called pre-stressed concrete cylinder pipe, or PCCP. It's a composite structure that combines the compressive strength of concrete with the tensile strength of steel. Here's how it works. First, a robust concrete core is formed, the structural foundation of the pipe. Next, a thin steel cylinder is embedded within, acting as a watertight barrier. Then comes the critical layer: high tensile steel wire, helically wound around the cylinder under extreme tension, up to 200,000 pounds per square inch. This pre-stressing wire counteracts the internal pressure of the water. Finally, the entire assembly is coated with cement-rich mortar, protecting against corrosion and environmental damage. Each finished segment measures 4 meters in diameter. That's 13 feet, 7 to 7.5 meters long. Wall thickness, 25 centimeters, and each one weighs between 73 and 80 tons. 2 factories were built specifically for this project, one at Brega, one at Sahara, together producing up to 80 pipes per day. At peak construction, they manufactured over 500,000 of these segments. The numbers become almost abstract at this scale. The steel wire used in manufacturing, enough to circle the Earth 280 times. The aggregate materials, sufficient to construct 20 Great Pyramids of Giza. The cement alone, 5 million tons, could pave a highway from Libya to Mumbai. But building the pipes was only half the problem. How do you transport 500,000 concrete cylinders, each weighing as much as a commercial aircraft, across the Sahara Desert? The answer: you build your own infrastructure. Standard Libyan roads couldn't support the weight, so engineers constructed over 3,700 kilometers of dedicated haul roads, purpose-built routes running parallel to the pipeline trench, just to move the pipes from factory to installation site. At the project's peak, 300 purpose-built pipe transporters operated around the clock, day and night. The total distance traveled by these vehicles over the project's lifetime? Equivalent to a round trip to the sun. Installation was equally monumental. Trenches were excavated 7 meters deep and 7 meters wide. Specialized cranes lowered each segment into position. Bulldozers nudged them into alignment. Giant rubber O-rings sealed the joints, followed by cement grout. Then the trench was backfilled, burying the pipeline beneath the desert. In 1989, water reached the first reservoir at Ajdabia. In 1991, Phase 1 was officially completed. 1,600 kilometers of double pipeline connecting the Sahara and Tazurba well fields to Benghazi and Sirte, capable of delivering 2 million cubic meters per day. Phase 2 followed in 1996, bringing water to Tripoli. Phase 3 was completed in 2009. Today, the system delivers approximately 2.5 million cubic meters daily, 70% of all fresh water used in Libya. But there's a fundamental question embedded in this engineering triumph, one that becomes more urgent with every liter pumped. Where does this water actually come from, and will it last? The Nubian sandstone aquifer system is the largest known fossil water aquifer on Earth. It stretches across 2 million square kilometers beneath Libya, Egypt, Sudan, and Chad. Its reserves are estimated at 150,000 cubic kilometers, roughly equivalent to 500 years of the Nile River's discharge. But here's the critical detail. This is fossil water. It accumulated during the Pleistocene epoch, during ice ages, when the Sahara was green and temperate. Rainfall percolated into the sandstone formations over millennia. Then the climate shifted, the rain stopped, and the water has been sitting there, sealed ever since. Under current conditions, hyper-arid, with negligible rainfall, the aquifer receives effectively zero recharge. As one U.S. Geological Survey hydrogeologist put it, the modern replenishment rate is effectively zero. This is not a renewable resource. Libya is mining water, and estimates for how long it will last vary dramatically, from 250 to 650 years, depending on extraction rates and calculation methods. The pipes themselves have a designed lifespan of approximately 50 years. They'll need to be replaced twice per century. The water cannot be replaced at all. In 2011, Libya's political order collapsed, and with it, the infrastructure that kept the country alive. On July 22, 2011, NATO aircraft struck the Brega pipe manufacturing plant, one of only 2 facilities in Libya capable of producing the PCCP segments, essential for pipeline maintenance and repair. NATO stated the factory was being used as a military storage facility and that rockets were being launched from the site. Project officials disputed this characterization. What is not disputed, major sections of the plant were destroyed. 6 security personnel were killed, and Libya's capacity to repair its water infrastructure was severely compromised at precisely the moment the country descended into prolonged civil conflict. In the years since, the system has suffered from neglect, sabotage, and chronic underinvestment. Armed groups have seized control of well stations. Illegal connections have proliferated. Maintenance has been deferred. Today, the Great Man-Made River Authority continues to operate what remains functional, posting updates on social media about repairs, outages, and security threats. The system still provides water to millions, but its future remains uncertain. The Great Man-Made River represents something remarkable in the history of engineering. A developing nation, largely isolated from international capital markets, financing and constructing the largest civil infrastructure project ever attempted, without external loans, using domestically manufactured materials, employing increasingly Libyan expertise. It moved water across 1,600 kilometers of desert. It turned arid land into farms. It provided 70% of a nation's freshwater supply. But it also raises questions that extend far beyond Libya's borders. What does it mean to build a civilization on a non-renewable resource? What are the ethics of consuming water that took 1 million years to accumulate, knowing it cannot be replaced? And what happens to the cities, the farms, the millions of people who now depend on that water when it begins to run out? The Great Man-Made River may be one of humanity's greatest engineering achievements, but it's also one of its largest gambles, and the clock is already ticking. If this story made you think differently about water, infrastructure, or the hidden engineering that keeps civilizations running, consider subscribing. We explore the world's most ambitious construction projects, the ones that push the limits of what's possible, and the ones that force us to ask whether we should. Hit the bell to get notified when we publish. And if you have thoughts on the Great Man-Made River or know of another mega project we should cover, drop a comment below. Thanks for watching.